Yeah, so I'm Jason, co-founder, CEO of ZKonduit that makes EZKL, which you can install in Python. So let me start by talking about kind of why we're here, right? So to me, what's exciting about applied cryptography and ZK in particular is that it's a way to change the set of equilibria, social, economic, and political equilibria that we can have as a society, right? So the first example of that is something like a non-inflationary currency, Bitcoin and Ethereum, a problem a government can't solve, but we can solve that kind of collective action problem with cryptography. But I think we're just kind of getting started on what that unlocks. And of course, solving collective action problems, solving tragedies of the commons is not just a sort of idealistic political thing, but unlocks a tremendous amount of value, right? So that's kind of, to me, the biggest picture. But we still have to search that space, right? It's not just given to us. What we can do is create tools that let us explore it, but there's still a lot of work to do in terms of finding out how to fill that in. And so a couple of observations. One is that, of course, AI can help us search that space, both sort of upstream in terms of getting things coded, but also in the sense that, you don't always have to code something. You can train a model, right? And you can delegate things that used to have to happen at a human level, judgments about whether a task was completed, or adding further intelligence to a smart contract, letting it be a judge, and so can tighter development loops. And so mostly what I'll focus on today is talking about how we're trying to improve the development loop in using AI on chain, and in general deploying ZK with EZKL. So what our approach is 3 steps. So you specify the logic of your app or your AI model in ordinary Python. And right now that's a small subset in the sense of mostly it's any PyTorch and a few other things. But as time goes on, that's going to be more and more general Python. Then we used Rust and Halo 2 to ZK it. You're free to dig into the details of how that works if you want to, or to ignore them if you don't want to. Of course, lots of type systems and everything else to give good security guarantees and to make us comfortable with that compilation step. And then we help you deploy it with a Solidity verifier or a native verifier or a WASM verifier, and you can use TypeScript and JavaScript to prove or verify. And increasingly what we're doing for our customers is to handle the proving servers and the ZK artifacts. We can do that for you if you like, and if you don't, you can run it yourself because it's all open source, Apache licensed. So for me, the big picture of ZK is that a ZK proof is a programmable signature, right? So we have a secret key, we have a public message, you apply a signature algorithm, and you get out a signature. Anyone can check, the chain can verify that, or anyone can verify that that's true, and believe that you really ran this algorithm and this data. What a zero-knowledge proof is it just lets us replace that fixed signature algorithm with any program we like. Now we have arbitrary private inputs. Maybe it's a password, maybe it's a secret key, maybe it's a face. We have arbitrary public inputs, maybe it's a time series of data. And we get out a proof, and it has a similar security properties to a signature, right? It's possible, it's probabilistic, it's possible that we'll get it wrong. It's also possible you can mash in your keyboard and guess Satoshi's keys, but we're comfortable with that level of probability, right? Okay. What is zero-knowledge machine learning? It's just saying, okay, we're going to drill down any program. Instead of any program, we're just going to focus on model inference for now, right? Forward pass of a computational model, application of a statistical procedure, and as I was hinting at, we're starting to get to more general things as well. But mostly inference because training is too expensive. The overhead to inference while coming down is still so high that doing training inside of proof right now doesn't make a lot of sense, in my opinion. Okay, so what does that look like? This is just to specify a model. It's just Python. You're initializing something. You're defining a forward function, some convolutions, some relus, just ordinary PyTorch. And you can see you can throw in some additional cryptographic data. So for example, here we throw in a key or a public key, and then the proof that would be produced for this is our an example of like our singing model where we have a thing called crypto idol where you can sing to the computer and it uses ZKP to rate you. Takes only a second or two to run. And this key blocks the front running. So that means that the proof is tied to your public address, your Ethereum address. No one else can intercept that and get your rating. So you're able to sort of throw in additional cryptographic information as well as use ordinary PyTorch. And increasingly, you can do other things. So this is an example of a gradient-boosted tree. So you can pull things from scikit-learn, and then EZKL will also compile that to a proof for you. Okay, so like I was saying, we're kind of getting to a place where we're increasingly general, just sort of some Python application logic that we compile into a zero-knowledge proof with Ezekiel, and this is kind of forward-looking in the sense that we've got a lot of it deployed, but not arbitrary Python yet, and we're looking for sort of people to collaborate with on things you might want to write that way. Why? Well, okay, here's a chart of programming usage by the developers. Python is quite a bit larger than Solidity, which is in turn quite a bit larger than CIRCOM or Halo 2 or any of our specialized ZKP languages, right? So if we want to onboard tons of developers, if we want to explore that space of collective action problems that we can solve as quickly as possible, we want to access this JavaScript, Python, TypeScript world, right? To get the most people thinking about this and experimenting as we can. So our approach is, as I said, to compile to Python, but also to let you do everything if you want from a Colab notebook. So you can, and a lot of our users today use Colab notebooks to iterate on the proof system, or iterate on the thing they want to prove, the forward pass of the model. And also in there, we can do all the other steps that we need. So one of the problems people have had is calibration. So there's a lot of knobs you can turn in Ezekiel or in a zero-knowledge proof to change the trade-offs, right? Like, how many rows do I want to use? What kind of quantization settings do I want to use? There's a lot of choices to make. So we have some amount of automated calibration that you can use. And you're still free to tweak those further if you like. Those can be done from Python. You set up the circuit, also from Python. That means you're creating a prover-verifier pair, or you're creating the artifacts, proving key, verification key, etc. Fixing the model. And then you can prove. You can create a EVM verifier or the artifacts for native verifier, like a WASM verifier, and you can deploy and check verifications to any RPC. This is using a local Anvil right from Python or from your notebook. So we think that's an interesting developer experience that really reduces the amount of kind of pain and bondage and discipline that we usually encounter with writing zero-knowledge proofs. And lastly, and you can see this is bleeding edge because of our beautiful CSS, you can prove and verify in a mobile browser. Even on my terrible old iPhone 11, we're talking about hundreds of milliseconds for the proving and the verifying. Of course, that goes up as the model gets more complex. There's a limit on what we can do with WASM. WASM is a daily battle to make it behave, but try it out. If something doesn't work, let us know. So we can either verify using a deployed contract, like we're spinning up an EVM inside the browser and verifying there, which sounds crazy, but it's actually reasonably quick, a few hundred milliseconds, or we can verify natively, which is a bit faster, or not natively using WASM, which is a bit faster. So we're moving to an experience where you work in Python to define your problem, you deploy to JavaScript for the actual application development. And the really bleeding edge, totally beta thing is that you can just pick a model and some sample input. You can upload it to our service cloud offering, and we'll do all the steps for you. So if you want to try that out, just let me know, and we'll onboard you to that. Okay, so one question people ask: how is this practical, right? Like, how big of a model can we actually do? A year ago at SBC, we did the first demo of proving a small MNIST model with an EVM verifier. We had to use an aggregation proof. That was about 12,000 flops. The circuit was hand-coded by me very badly. And it took about half an hour and a 540 gigabyte server, 540 gigabytes of RAM. Okay. A year later, that same proof takes about less than a second and 100 megabytes on a laptop to prove. Okay, so things have gotten really fast. We can do it on the phone. I like to think about this in terms of floating point operations per proof. So that's kind of a nice metric. We heard about energy, which I think is probably a better metric, but I love this idea of just how many floating point computations or floating point replacements are we cramming into one proof? Some measure of how much intelligence, how much roll-up is happening. And what we've gone from is in September of 2022, around here, 10,000, to a year later, we're actually out here at 1 billion floating point operations per proof. We talked about this one, the 2023 model has also with an EVM verifier, about 1 billion flops, compiled from Python with Ezekiel, no handwritten circuits, done by folks that are here. So but the Noya folks. So all done by someone else using Ezekiel, who's using Ezekiel in production. So the thing I really like about this is I don't even know what that model is. I don't have to know what that model is. Somebody else can write it and compile it and use it at that scale. Now, 1 billion flops is actually not that much for an AI model. So we still have a ways to go, but it's still, we're still happy about it, right? Okay, so how do we do that? Combination of several factors, not the sexiest factors, to be honest. Just kind of roll up your sleeves engineering, changing the arguments, improving the algorithms, parallelization, changes to Halo 2 that got upstreamed, changes to some of the arguments there to make them more friendly to parallel work. And really for us, the focus has been on developer experience, getting something that's easy to use, getting it in people's hands, and learning what it is that they get stuck on, or where the hot points are, what's slow, what's running out of memory, what's dying, and then we fix those things, and it gets better. So far, this is without using GPUs or FPGAs. Yuval and I have been talking, and I hope next time you hear from me, that won't be true. We'll have something with Enganyama. And this is without using improved lookups or folding, which are also on the horizon. So as those things come into production, we'll add them. So we still have some ammo left in terms of speed ups. Okay, so another question, of course, you want to know is, what models am I allowed to use, right? Is it just multi-layer perceptrons, or are there other things? And so that's what we started with, is multi-layer perceptron, that's the MNIST thing, and convolutional neural networks, so a variety of PyTorch models off-the-shelf work. We can do transformers, small LLMs, NanoGPT, for example, which we launched a few months ago, and we've gotten that was sort of server side, now it's laptop, about 12 times faster than the first version. Self-attention, multi-head attention, and all of these examples are in our repository. If you want to run them yourself, go for it. Decision trees, random forest, gradient boosted trees, stuff from scikit-learn. Classic statistics and data science, working on a project with EF to look at sort of descriptive statistics and classic sort of scikit-learn type things. If something doesn't work, tell us and we'll fix it for you. We'll get it running, usually in less than a day. Not an SLA, but we'll try to get it in less than a day. So lots of things work. It kind of happened that we were building lots of modules and components, and then we hit some sort of critical threshold where most things started to work. So that's where we are now. If something doesn't work, it's a bug. Tell us, yeah. Okay, the other thing to think about is kind of, of course, a zero-knowledge machine learning model in isolation is not a crypto system, is not a smart contract. You have to build some kind of broader system around it. And so we're rolling out some more tools to do that. Basic primitive operators like Booleans, is this thing equal to that? A gate that's an AND or an OR gate. Set membership, so you can do kind of a small brain semaphore type thing. And more exploration, sort of that general circuit writing. Another thing that we have is the ability to change the visibilities of your parameters and your inputs. They can be private, public, hashed with Poseidon. Private hash, which means you take it, private input, you hash it, and you push the hash thing through the circuit. That's useful for something like a set membership. And encrypted. So this is like, if you want to commit using Poseidon to some weights or some inputs, this is if you want to use the native KZG commitment. You call the parameters public, and that gives you a fixed column in Halo 2, which is of course much more efficient. Here are some of the notebooks we have right now in our examples that show some of the things you can do. Please check it out. You can load all of these in Google Colab. Okay, so the other question everyone has to ask, of course, is this, because we're in crypto, but by this they mean actually when do we get LLM tokens? When can we actually see, when can I run intelligence on chain? Not today, but maybe soon. Okay, so as I said, right now we can compile LLMs and transformers really well. Relatively small models provable. We're about 10 or 20 times faster than we were when we first announced that, but that's still, we still have a ways to go. I estimate so far we're getting about 3% performance improvements a day on average. If that continues, big red if, okay, if that continues by some succession of miracles that continue, we could get to Llama 2 maybe by the end of the year, I'd say, or like next year, I would be kind of surprised if by this time next year we don't have something that we can show you where we've run a big LLM, but don't hold me to that, not investment advice or anything. Okay, so how fast, of course, it's very hard to answer that question. It depends on your settings, it depends on trade-offs that you make, it depends on the model and the machine. For most purposes, it's fast enough for production, actually. It's fast enough to get under block time for a lot of calculations. For more big models, it might take a bit more time and a bit heavier servers. If you wanted to run, if you want to run Llama on your phone, no, But if you want to run some simple things on your phone or some reasonable things on your laptop or some big things on a server, sure. Yeah, and so the last thing I want to talk about is just where we're trying to go with developer experience. That's very, very important to us because I think that's the key to kind of unlocking that solutions of collective action problem that can happen with ZK. One perspective is where we are right now is that you really have to be an expert to write circuits. You might have to learn a custom language, translate your ideas to that, really think about circuit writing. I find that fun. I was a mathematician. Not everyone finds that fun. Even for those of us who find it fun, it's slow, right? Spend some time writing it, figure out a verification. A lot of times the newest models, for us, we're very obsessed with EVM verification. A lot of the newest methods don't have that yet, so that's a story. Then you have to hook everything together with Solidity, prover, verifiers, JavaScript so that you can deploy the app, maybe spin up some big, giant proving servers. And then one of the more subtle problems that people run into as you start to really scale this up is managing artifacts. So you have all these proving and verification artifacts, keys and hashes and inputs and outputs. This is cryptography, so if there's a mismatch, you're like, okay, I've got this random looking string and I've got this random looking string and it's the wrong string, and that's all I can tell you, right? So everything explodes, you feel like, Indiana Jones, and we're trying to make that a little bit less painful. So this is our goal for the EZKL experience. The insane thing is that you can do it all from your phone if you want to, because of the collab and everything else. You can create a model, deploy. We can optionally handle managing these artifacts for you, and we're trying to make that a little bit easier. Prove and verify from a mobile browser. And again, this framework is opinionated. We're making choices and we're narrowing things down, but it's flexible. You can use the command line interface. It's all Apache 2.0, so you can just use the open source Rust library directly. If you want to write your own circuits using our stuff, you can fiddle with the settings. You can get as deep as you like. If you get really deep, we'll probably try to hire you. But anyway, so now it's 100,000 times faster. That number was, by the Node folks, that was 3 weeks ago. So we probably picked another 2 to 20x improvement since then, just on some models. So yeah. And lastly, as I said, this is really, I feel, a project made in collaboration with you, with the community. We get a lot of feedback, and every piece of feedback we get really helps us improve. So if you try it and it doesn't work, something breaks, something's slow, something does something that you're not expecting, please tell me, please tell us, we'll fix it. Check out our GitHub and join our Telegram if you like. That's all, thank you.
Do we have the mic for questions? Okay, great. Does anyone have any questions for Jason? One up here in the front.
Thanks for the talk. You mentioned having smaller models within like a single slot time on Ethereum, for example. When we get to the point where you have sort of larger models you could do in a single slot, what are some of the cool stuff you think people could start doing on-chain?
Yeah, I guess a lot of the stuff that first comes to mind is kind of financial DeFi related. You could write a roll-up this way if you really wanted to. It's sort of nuts, but you can do financial computations. I'm really excited about on-chain gaming, for example. It's one of the things that probably would be a push going forward. That's something that is going to have by far the best user experience if you can get inside of a block. And then what you're doing is you're sort of using EZKL as a physics engine. You have a state of the world, and you're proving that your update of the state of the world is valid, and then you're submitting that, right? So that has a lot of fun kind of decentralization things too, where you can have, everybody owns a part of the planet. It's like a Minecraft ticks. Ticks are being computed, and anybody can perform the tick, or only certain people can do it. So that's an interesting application, but yeah.
We got a few questions in the back.
Likewise, thanks for the talk. I just wanted to ask if you could share a little bit more about the compilation pipeline and how you're actually going from all the different models. Is there an intermediate representation like Onyx, or are you using something else more?
Yep, it's Onyx. It's Onyx. So what we do is we compile, or we ask the user to compile their model to Onyx, and then we ingest Onyx and perform some sort of simplification steps, rewriting things in terms of some primitives, and then lay those out into the circuit. And part of that, a lot of that process is stuff like making decisions about the quantization strategy, because quantization is kind of we're using fixed point arithmetic. What comes to us is floating point arithmetic. In the beginning, that caused some problems, but right now, I think our error rate is quite low. It's like often less than 1% or even less than 0.1%, using kind of increasingly thought out quantization strategies. So yeah, Onyx to circuit gets laid out.
Yeah, thanks for the talk. Impressive results, especially also with regard to MNIST. I know, like, depending on what activation functions you use or how many neurons, like, it could blow up in the constraint size. So I was just wondering, could you talk more about what optimizations you use? Like, do you do feature preprocessing or maybe certain activation functions which are more efficient?
Yeah, so we're not doing anything particularly special with the activation. We're just using lookup tables, which don't really know whether you're using ReLU or sigmoid or what. A lot of the optimization is kind of in rethinking the argument, right? So you can make you can compute the same basic arithmetic, matrix multiplication in many different ways. You can lay it out in many different ways. Halo 2 is, I think, a great system, but it's very easy to shoot yourself in the foot. So you kind of have to explore the space of different ways you can express a computation, and oftentimes the thing you think is going to be fast is not. And the thing that, so you rework it, you try different layouts. So for example, we use accumulation arguments a lot, right? Where you have 3 columns, you have an input. If you want to take a dot product, you have vector X, vector Y, and then a running total. And that's much faster than, for example, sticking it all in one gate or using rotations. That's an example of. And then we have stuff like column overflow, so that you can spread out a computation over multiple columns if you want to reduce your number of log rows, and therefore the time to compute MSMs. And all these things kind of give you dials to change the performance trade-offs.
Okay, thank you.
Yeah.
Okay, I have one question. I assume there's no deployed on-chain verifier for anything like this today, or are there deployed verifier contracts for ZK?
Yeah, there's deployed verifier.
So can you give me
it's 400,000 gas.
Okay, cool. That's what I was going to ask. Is the
about 400,000 gas. A bit more if you use an aggregation, but simple verifiers are around 400,000. Each one is a little bit different because it depends on exactly the circuit parameters.
Got it. Okay, that was my question. Thanks for answering. Any final questions? Okay, great. Thank you very much.
Thank you.